we are delighted to announce the online S3 online talks consisting of 2 invited faculty talks scheduled for this week. As for the first talk, we are glad to have Dr. Saikat Chatterjee, a faculty of School of Mathematics at IISER TVM. He completed his PhD in mathematics at SN Bose National Center for Basic Science, Kolkata, India, on 2011 by writing a thesis on study of path spaces, gauge theory, and holomony. And he joined IISER TVM on 5th May of 2015. His primary research lies on differential geometry, higher category theory, and mathematical thesis, so mathematical physics. Ongoing research fields are connection of categorical bundles, Gabor, Poisson geometry and geometrical quantization, and complete sympathetic geometry. We are looking forward to have an exciting session this afternoon, and I welcome the speaker on behalf of all participants and the club. For the participant, do put your questions in the chat box or unmute your mic at the end of the session to interact with the speaker. I'll let Dr. Chatterjee to take over from here.
So, title of the talk is Semidirect Product of Categories and Schur's lemma for categorical representations. What is the definition of a category? So, if I say that there is a category C, that basically means I am given a pair of, you can think of sets. There are some technical issues, but for the time being, you can think of a set of objects and set of morphisms or arrows that will be denoted. This is just to introduce the notation. I will be denoting the set of objects by this notation and arrow set or morphism set by this notation. Along with this, there will be a pair of maps from the morphism set to the object set, which are called respectively source and target maps. And there is also the identity map in the other direction. So given any object, with that one you can assign an identity, or it is called an identity arrow. And then there is this composition map. So I do not know, are you familiar with this notation? Otherwise, just let me explain what this notation means. So this notation means, this one I write. So my writings are clearly visible, right? I mean, you can read it, or is that fine? Okay. So when I use this notation, see, we already have said that there are source and target maps from morphism C to object C. So here is source and here is the target map. So you can basically take the, what it is called, fiber product or pullback to construct this set. This is usually written in this fashion. So if you want to write this explicitly, so this set basically means it is simply the set of all pairs in the Cartesian product of mod C times mod C, such that source of one map is coincides with the target of the other map. So F2, F1 both belongs to the arrow set. So you can see that that's why it's basically called composition. So if I give you two such pair, you should be able to give me another composed map, which I denote by this F2 small circle F1, and this should satisfy. So I'll erase this part because this is just to explain the notation. So the source target maps are compatible with the composition map in the sense that if you take the composition of F2 and F1, F2 and F1, then you find the source of this map, then it should be same as the source of F1. And similarly, if you take the target of F2 compose F1, and sorry, this should be target of F2. this should be the same as target of F2. And along with this identity map, so here this F is from A to B. Okay, let us not write that. So here source of F is A and target of F is B. If this is the case, then if you compose this identity morphism with that one from the right, 1A, then you will get same F. Also from the left hand side, if you compose with 1B, that will give you the same F. So let us see, let us put this let us draw some diagrams. It will be probably easier to understand. So you can basically think of an arrow or morphism in a category like an arrow. You can represent this like an arrow with source. So if you represent this arrow by F, so if this arrow is F, then this is some arrow from the source F to target of F. So when you are basically composing these two arrows, you are basically taking F2 from here to here, and you are taking another F1, or maybe I have written in the other direction. Is it that always happens to me? So this is, let us okay, yeah, probably I should have stick to my convention, so I should write this as. And now suppose you have another morphism whose source actually coincides with the target of F1, then actually you can compose these two. And this is precisely the composition, and that should give you this composed arrow from S of F1 from T of F2. And precisely see that this is the condition I am talking about. I am representing this as a diagram like this. So with this picture in mind, we can construct some examples. So yeah. So let us, typically, I mean, everything in mathematics can be described in terms of the of a category. So for example, you take the category of vector spaces. So this, if you denote this category by vect, so object of this vect is vector spaces. That means an element of this set is actually a vector space. And as you can probably guess, the morphism set will be the linear maps. Right? So because if you have a linear map, let's say T1 from V1 to V2, and another linear map from T2 to V2 to V3, you can compose them, right? The composition is simply the composition of your sets. So of course, category of sets is also, you can also define the category of sets. Again, there is certain catch is there, foundational issue, but let us not get into that at all. So, but the rough idea is this. So, or you can consider similarly category of groups. So this, if you denote by this GRP, so object is your group. So that means an element of this set is a group, and as you can guess that again this an arrow is a group homomorphism. So sets, of course, yeah, as I mentioned, that set is also a, you can consider the category of sets. Another more trivial example you can consider. So suppose S is a set. you can define a category which is sometimes called a discrete category over this set S. So object of this, let us write this category to be S bar. Object of S bar is simply S, and morphism of this category is also again S. So this will give you, trivially, it will give you a category. Similarly, if you're instead of S, if you take a group, you can also consider the group, a category, discrete group category. So now let us, okay, so one more thing, let us introduce here. So in mathematics, of course, when you define something, then you also talk about the maps between such objects. So for example, in the category theory also, so let C and D be a pair of categories. Then a functor, let's say if it is written like that, is a pair of maps. So this map, as you see, that a category is not the more familiar object that you might have encountered in mathematics so far, like groups and all these things. They have an underlying set. So in category theory, actually, in some sense, there are a pair of sets. So for both these pairs, so one is object and one is morphism set or arrow set, you will have, I'm denoting both of this map by the same notation, but of course they are mapped between two different sets, two different pair of sets. Sorry. And they should respect the composition. That means F to compose F1 should be. So you see here within the bracket, this composition is actually happening in the category C, whereas this entire thing is happening in the category D. Of course, this is in C, so that means F will take this to the category D, and also on the identity map, it should satisfy this relation. These are all very natural conditions, as you can see. So this is the notion of functor. There is something even beyond functor that are called natural transformations, but let us not go into that at the moment. I do not know. I even probably the latter stage of this talk we may need. Then we will introduce early. So this is a functor which defines a map between two categories. And now, let us again consider some simple examples. So I don't know, some of you might have done a little bit of algebraic topology and at least fundamental groups that you need, right? So you see that in the fundamental group, you can actually think this pi as a functor. Pi, usually that is a notation you use. What is the notation that you use? So this is, you take a topological space X. So let X be a topological space, and X is a fixed point. You fix at some point in X, then pi x x, and if it's simply connected, then it does. Sorry, if it's connected, then of course it doesn't matter. But this is your fundamental group. Of X at X, and now they have this nice relation. If X to Y is a continuous map, let's call it F, you know that induces a such that X goes to, let's say, F of X. So then it induces a group homomorphism, right, which we denote sometimes by F star. So right, so this F star is a group homomorphism. So this is a continuous map. This is a group homomorphism. Moreover, it actually respects the it actually respects the composition. This induced homomorphism. So by that I mean that if you have, let's say, x to y and y to z, you have, let's say, suppose this is f and this is g, so you can compose this to continuous map and get a composition x to z, g compose f. So that means, first of all, we are basically talking about the category of topological spaces, right? So here objects are topological spaces and arrows or morphisms are continuous maps between them. Similarly, if you go to a higher level like smooth manifold, you can talk about the smooth maps and blah blah blah. So now you have this decompose f from x to z, and this induced homomorphism actually satisfies this nice property that if you compute the induced homomorphism of this composed map, they will be given by this relation. So now basically I can see that this pi, I can view this as a functor from category of topology, sorry, not the category of topological spaces, but category of pointed topological spaces. You know what is a pointed topological space, right? You just fix a point and the arrows are basically continuous maps which preserve these points, in the sense that, so suppose, yeah, let me write this. So suppose x and x is an object in this category of pointed topological spaces, and y is another such object, then a map, then an arrow or is simply a map from x, continuous map from x to y, such that y is f of x. So that is all you have to do. Then in that fashion, this pointed topological space, we have the category of pointed topological spaces. So now, then this pi can be viewed as a functor here, right? So how I am defining this pi? So this is to what? Pointed topological space. To anyone can suggest what should be the right hand side of the categorical group? I'm sorry, what will be the right hand side category? Not those who have done the category theory course and all these things. So someone just probably maybe first time seeing category theory. Can someone respond?
It is the groups.
Exactly. This will be to the category of groups. Very good. So you basically take any object here. An object here is a topological space along with a point, a specified point on this topological space. So you take an object in this category. That means a topological space with a specified point, and this you send to simply pi, the corresponding fundamental group, right? So, and as we have seen that this pi, if you can define this, let's say this f like something like this, something like this, an arrow in the pointed topological category of topological spaces, you send this to the corresponding induced homomorphism, and then you see that precisely this condition is satisfied by this thing. That is what we are saying, that by this property, right? So this you can view this as a functor. So functor also comes very naturally in the mathematics almost everywhere. Okay, so this let us stop on about the category theory for the moment. So let us do another one more thing. Let us introduce that is called categorical group. So a categorical group, first of all, is of course a category, and here, roughly speaking, I am not very precise here. So basically, both object set and morphism set both have to be groups. And then you the structure map. So I have used this word structure maps. The structure maps are basically these maps defined on a catalog source, target, composition, and all these things, right? So identity map, all these things are structure maps. So all these things are basically group homomorphism. And then this composition has to be so okay. So I probably I should explain my notation here. So here when I am writing a circle between two such arrows, it basically means composition defined on a category. And when I do not use anything, I'm just juxtaposition of two elements. So basically, if I write G compose F, that will mean first of all that you have to make sense of this thing, right? Otherwise composition is not always defined. So if I have a continuous map from X to Y and another map to W to Z, you really cannot compose them. They have to satisfy the condition, this source target compatibility. The target of one arrow should be the same as the source of the other arrow. Then you can only compose two such arrows. So when I write G compose G circle F, I basically mean that G and F, they are two arrows and they fulfill that condition. That target of F is basically source of G. And then you have G compose F. So this is the meaning of the categorical composition. This is my meaning of my notation. But when I am writing, let's say G prime like this basically means the group product in my categorical group, right? So of course this thing may not make sense in a general category, but when I am talking about the categorical group, both object sets and morphism sets both have group structure. So you can take two elements and sorry, take their group product. So without when I do not use any notation, just write two symbols side by side, that would mean that I am taking the group product. So with this notation in mind, so this has to this categorical composition has to be compatible with the group law that you have there. So you see here F2 compose F1, you take the categorical composition, and on the other hand you take F2 prime compose F1 prime, then you take the group product here. Of course this group product makes sense because they are the group product is in the group of morphisms. This should be same as if you take, basically it is called the exchange law. You can exchange this F2 and F2 prime and F1 and F2 prime. Then you can write F2 compose F2 group product F2 prime, composition F1 prime. So with this is just some technical reason this is here, but you can, for the time being, you can keep this in mind that this is a category whose both object and morphism sets are groups, and all the structure maps involved are group homomorphism, and they have some compatibility relation between these two, this categorical composition and the group product. So let us work out some simple example. First of all, take any group. Someone has asked a question, is it? Yes, Kalin. So yes, this is well defined. That is assumed. Whenever I am writing this as a composition, I always do not mention that G and F. This thing is happening. This composition is well defined in the sense that target of F1 prime is same as the source of this F2 prime. That follows from the fact that S and T both are group homomorphism. Okay, so because these are both are group homomorphism, so this condition is met. But whenever I write decompose F, I actually, the underlying assumption is yes, that composition makes sense. But in this case, yes, as you have rightly asked this question, but yes, that it may not have, but this will follow anyway. So most simple example, you can take any group. Let G be a group. So then I defined that, as I have said, that you can consider the discrete category of groups. So I define another category, let's call it G bar, whose objects are is G, but again, don't confuse this with the category of groups. Here you see the difference, you see, right? Earlier when I say the category of groups, an object in this in this category was actually a group. And here the entire object set is a group. That means an element or an object in this category is actually a group element, right? And you can also take this morphism of G bar to be simply G. So how do you, so what is the source target map? So of course, trivially both are groups here, right? Source target maps are simply nothing there. There is no structure there. So if I give you any G here and target G, everything is G basically. And you can define G, compose G is G, and of course they have the natural group product. So this gives you this gives you a categorical group. You can also easily check that it will really satisfy the compatibility condition. So now another simple example with the group itself you can consider. So if you take G, again a group, you can define object of say another category. I am defining the scripted G. So is G, and let's say morphism of G is G cross G. With that, so if I give you an element in this morphism, say this G1, G2, so you define source to be G1 and target to be G2, and when you compose, the group law is simply given by the direct product. This is simply given by G3, G1. So this again gives you a categorical group. So yeah, but the one example that is crucial here, rather that completely classifies the categorical groups, that is called something called cross modules. I don't think I will have the opportunity to actually use this thing, but still, so any categorical group, a categorical group is same as a cross module. So what is a cross module? So a cross module is basically given by a pair of groups GH along with this homomorphism, group homomorphism tau and alpha. So what is tau? Tau is a group homomorphism from H to G, and alpha gives you an action of G on H, and they together they should satisfy certain compatibility relations. So these are this is G tau H G inverse, and so this, if you give a categorical, if you give this system of information, a pair of groups, ordinary groups, and this homomorphism, pair of homomorphisms satisfying these two relations, I can always obtain a categorical group by defining object of this category to be simply G, and morphism of this thing to be the semi-direct product of H and G with respect to this action alpha. So other details that I don't want to write at this stage. So now let us move on to the other part of this thing, and at the classical level, that is called what is representation of a group on a vector space V. So a representation is, I do not know how many of you have seen representation. Probably yes. That's why this is very basic notation, elementary definition. So I will be talking about representation on a vector space. So suppose G is a group, then a representation is a map from G cross V to V, such that for every G, so here this notation is clear, right? What I mean is, if you keep a fixed G element small g in G, that will give you a map from V to V, right? So this is a map from G cross V to V. If you keep one element fixed, that will give you a map from V to V. That should be linear, and this row E should be the identity map on the vector space V. So, and equivalently, one can write this as a more elegantly, that a representation is a group homomorphism from G to the automorphism group of V. So you see that if I keep the group fixed, now I will not change the group. So for a group G, a representation is basically this pair, right? Rho and B. Suppose you do not bother to change your group. You have a fixed group, and if you talk about the representation of this group, you have to specify these two pair on which vector space you are representing this group, and what is this map. If you specify these two things, so that will specify your representation. So will be, when the group is fixed, we will be denoting a representation by this notation, rho comma V. V is the vector space. And so now the question is, natural question is, suppose you have a map like this, G cross V to V. Now you take a subspace of this V. Now you can restrict this map to this set, right? G cross W. So you get, there is no guarantee that this map is actually take you to W. In general, it will still be in V, right? It's not necessary that it will be inside W. You can restrict the vector space here on your left hand side, but it's not necessary that the image of this thing, it is not guaranteed the image of this thing will also be falling in this subspace. So, but if this happens, that there is a trivial subgroup, subspace means of course the zero vector space, proper non-trivial subspace W, such that this actually happens. I mean, the image of G cross W is inside W. Then you see that this gives you a representation on W on its own merit. So then this is called reducible representation. And if you cannot find for a particular representation any such subspace, then it is called irreducible. So now, as I have said that in mathematics, always if you define some object, you also want to define an arrow, a morphism between these similar objects. And that's why this when this category theory comes into the picture. So now I also want to define a map between a pair of representation. So it is simply given by, so suppose rho 1 v1 is a represent. Again, I am keeping the group fixed. I am not changing the group G, so I am not mentioning it here. So suppose group is G, and you take a pair of representation of this group, rho 1 v1 and rho 2 v2. So a map from between rho 1 comma v1 to rho 2 v2 is simply a linear map from between the vector spaces v1 to v2, such that they somehow intertwined with this representations that you have here, right? So let's see that these diagrams make sense. So you have one hand, you can take this identity that I have written. This is actually identity in group G. So you can define a map from G times V1 to G times V2 simply by taking given any G V1 to the G comma corresponding image of element under this F, and you have the representations, pair of representations rho 1 and rho 2 here, and this diagram should commute. So if you want to write this explicitly, then you will simply find this relation. Then this is called, this F is called, so F, an arrow between, or a morphism between two representation is an arrow between the corresponding vector spaces, such that this arrow satisfies these conditions. Done. So this is an arrow of arrow between two two representations, and now you can actually talk about the category of representations. So objects will be the representation. So I'm keeping the group fixed. Your objects will be the arrow, these representations on various vector spaces, and the arrows will be the maps between such representations. So you can also talk about the category of representation, and that often denoted like this. So again, so this is just to indicate that I have kept the group fixed, and now I am talking about all the uh, all the arrows between these representations. So now let us come back to the classical Schur's lemma. It's a very simple proof. I mean, any of you, if you go through this carefully, just do some diagram chasing here, you'll be able to easily prove this thing. Schur's lemma, the classical Schur's lemma. So this is called. So the thing is, suppose rho 1 v1 and rho 2 v2 both are. It's not right. What is b? Suppose both are irreducible representations, that means there does not exist any non-trivial proper subspace on which you can restrict this representation. And then if f is a map between them, so f either has to be a zero map or f has to be an isomorphism. So this, most of the time, subsequently I will only work with finite dimensional vector spaces, but this will this result is also true for infinite dimensional vector spaces. Everywhere it is true. So, but sometimes, I don't know, those who are probably familiar with Schur's lemma, that's why I want to mention, sometimes this is called the second Schur's lemma. There is another Schur's lemma which actually directly follows from as a corollary of the second Schur's lemma in the finite dimension. So that basically states, suppose I keep rho and v. I take an automorphism of for a fixed representation. That means I want to find an arrow from rho comma v to itself, rho comma v. Then if rho comma v is irreducible, then this has to be scalar multiple of the identity at v. But this holds, I mean, this holds slightly more generally, but this holds in the finite dimensional case, which you can prove easily from this thing. But there is another more important example of this first Schur's lemma, that it also holds in the countable. If the vector space dimension is countable, still it holds. But this is much more really non-trivial proof. This was done by Dixmeyer. So anyway, so let us move on. So this is the Schur's lemma in the classical setup. Okay, so now I will come back to the actual topic of this. So you already have spent too much time. So what I want to study here now, I want to study a representation of a categorical group. So let G be a categorical group. So first thing I have to, if I want to talk about the representation of categorical group, that means I have to talk about the representation where, I mean, there we had a natural choice and vector space. So here we have to talk about where we want to represent this categorical group. So again, the natural choice is you can have a generalization of your, like we have the generalization of categorical group, you can also take a vector space and you can talk about the generalization of a vector space and call it a categorical vector space. So that means the both object and morphism sets are both will be vector spaces, and all the structure maps, this is a category first of all, and where object and morphism sets both are vector spaces, and all the structure maps are linear maps. So this kind of setup I want to work with, but before that there is a catch here. So let us, I need to actually define an action of a categorical group. So what will be the natural choice? So take C any category, let C be any category. So you can talk about the action just by simply generalizing this thing, that an action is a functor. Here, of course, this G cross C, this is another category that you can, I mean, it has a natural categorical structure coming from the category G and category C. So you can define, so let's define, let an action of G on C be a functor like this. So this makes sense. Sorry, a functor such that both at the object and morphism level we have group actions. The meaning is clear, right? So when you are looking at the object level, so you are basically looking at this thing. This is a functor. So this gives you actually a pair of maps, not a single map, object of C to object of C, and another map at the level of arrows. Right? So this is a functor. So this is given by these two pair of maps. And now you see this object of G, as I have taken G to be a categorical group, this and these both are groups. So it makes sense to talk about the group actions. So if this happen, I can define, this is a very naive approach, but still you can, this definition makes sense. I will call it a action of the categorical group on this category C. But as I said, you cannot really construct many examples. So if as I have said, that a categorical group in some sense a very narrow kind of object, because it's completely specified by this cross module. So when you look at this framework, it's very difficult to construct any non-trivial good examples. So for that, what we could do, one way to do this thing, which is completely missing in the classical setup. So what I do, I will take two categories, A and B. So suppose A and B are categories. I want to define a category which I denote like this for the naming this notation. Other than being it a notation, there is not much sense. I'll explain that. So I want to define so here, yeah, I should mention here. The problem is when you basically take this to be direct product, then this structure becomes very restrictive, very strict, and you can only very few examples you can construct. So we can further relax this by simply taking, okay, so but still we want to actually talk about this thing, that object level we have an action, at the morphism level we have an action, this kind of things we still want to talk about. So what we can do, instead of taking the direct product of categories, I'm sorry, let us write this properly. So this is object A times object B, and morphism A times morphism B. Right? So what is there? So this is not this, but I don't want it to be a direct product. So how this thing is defined? Can anyone guess? Suppose I take A and B are two categories. I want to define this direct product category. How this composition will be defined? So if I take, let's say, G2 F2, and I compose with G1 F1, this most natural thing to do is define this in this fashion, F2 compose F1, and it makes sense. And this is precisely your category with the direct product. But I don't want to do that. But what I want to do, I want to keep the object set of this new category to be same as the direct product, and similarly for the morphism set as well. But what I want to do during composition, I want to I give a twist. So instead of, so object set and morphism set both remain same as the direct product category, but when you do the composition, I want to do, instead of directly taking this product, the idea is very simple. So you take G2F2, let us put some of S, let's say, and G1F1. I want to write this as G2 compose eta F2 compose G1 F2 compose F1. So what is this eta? So eta, idea of eta is that I want to define something which will allow me to talk about this kind of things. So that is precisely we are going to do. So okay, so let us make this thing precise. So this is the overall idea. So let again A, B, B categories. So suppose let eta be a map from, okay, let me check, I forgot the conditions actually. Yeah, eta is a map from, let's say, mod A times mod B. This map is only defined at a morphism level. This is just a map such that this has to satisfy these conditions. So first of all, so suppose K is an element, K is an arrow from object A1 to A2, and F is an object. So sorry, K is this is in morphism of A, and let's take F, which is from B1 to B2, which is in morphism of B. Then this eta Kf should be A1 to A2. So let us write 1, 2, and if you have a situation like this, again here I'm not talking about any group product here, of course. Here everything is in the general category level. So this should give you a splitting kind of thing. So can you see that this relation actually making sense by the condition 1, right? So this, and along with this condition that K1B should gives you, yeah. So what I was telling, that you see that this relation makes sense because when you take eta K F2 compose F1, the source target is basically as the same as the source target of the first entry here. So here the first entry is K and the source target is same. I'm sorry, here something is wrong. No, I'm sorry, this I have written completely wrongly. I'm sorry. This is wrong what I have written. So yeah, actually this will be yeah. Yes, eta Kf2 F1. Yeah, this is the right thing. So you see that eta Kf2 and K both have same source and targets, right? So that is what your first condition is telling, that source and target is completely determined by the whatever your first entry is. And then this has the same source and target as K, and here also this has the same source target as K, and so entire thing has same source target as K. And third condition is that if you have K2 compose K1, F is same as and eta 1f is 1a. Okay, fine. So all that is, suppose I am given such an eta, then what happens? Then I define a category as follows. So this is actually really non-trivial to check that this defines a category, but I'm not going to do the verification. If you want, you can do the, so here I can write this as an eta. You can do the verification yourself, and because this is just keeping track of the associativity and all these things. So you'll be able to work this out if you want. So I want its object set to be the same as object and morphism sets to be the same as the direct product of categories. But when I do the composition, so K2 F2, so with composition, compose K1 F1 is given as eta K2 F1 K1 F2 compose F1. So if you define this composition in this fashion, then you can verify actually that this also gives you a category. So this is theorem that the B is a category. So, but what we have achieved? What we have achieved is actually that we have a category now whose object sets and morphism sets are same as the ordinary direct product category, but the composition law is different. So how this will fit into the larger picture that we want to construct, the representation and all these things. So by the way, so I don't think I'll be able to finish this lecture today. So I'll stop in a while, and can I have another lecture maybe next week or something, whatever the convenient time, then I can continue there. Is that fine? As a part 2 of this lecture? Yeah, because there is no point in going further. I will just show why this is actually needed here. So you see here I have taken, and the first attempt that I have made in order to define a categorical action, I have defined a functor from G, direct product G times C to C, where G is a categorical group and C is a category, some category. So now instead of that, and we also wanted that, so we can talk about the action at the object level and the action at the morphism level. For that, of course, in the classical setup, there is no such thing as this kind of twisted product of between sets, right? So that I want that both at the object level and morphism level we should have this thing. So that I want to actually, that is my goal here, that I will replace this direct product by a semi-direct product. I mean, semi-direct product means this category. So I will take G semi-direct C. So what we will have in the object level and both at the morphism level, we will have the direct products. And so we could still talk about the representation, all these things at the classical level. But my condition for this functorality will be slightly different, because now I am not taking the direct product between these two. I am twisting this composition. So that is the main goal here, and then you can find this an interesting basically application to the, not application, but in a special kind of Schur's lemma. I mean the generalization of the Schur's lemma that I have mentioned in this framework. So I don't want to continue further. I just want to stop here. So if you guys are all interested, then I can have part 2 of this lecture. Because I don't have time, right? At 3:30 it's already, so I will not be able to cover anything. So I'll stop here then.